So this is module 1 we're going to focus on the basics of feature selection and the first kind, the filtering method. So we don't get time to cover feature selection in details in last Thursday's class on the general dimension reduction family. So this is a reuse of some of my last year's recording explaining the details of feature selection method. So let's get started.
Feature selection is a model selection. It's just I'm trying to select features. In the end, the derived model are different models if you think about it. So the task itself is we're trying to select P prime. So about this class, selecting P prime original features from the P features. Original features from the total P features, and there a categorical approach, and actually a lot of tools provided. They roughly fall into 3 categories called filter-based, wrapper-based, or embedding-based. And the goal in the end, if you think about it, is we are trying to improve generalization, right? If the task is classification, we're trying to improve the classification on the filter data. If it's regression, we try to improve the regression on the filter data. Sorry. And so there are some levels of differences. Do you select one feature at a time, or you select a subset of feature together? Then how do you select a feature subset from a set of P features? If you are still remember your algorithm class, select subsets from a set is a classic combinatorial search task. All right, so we already introduced a few examples about why we want to select P prime features from P features. This is really just a setting. You have the data matrix, P n times P, and then you try to select only that square, that smaller yellow block, P prime, and make the data it's much smaller, hopefully use smaller memory, less memory, and computation more efficient. So why do we do feature selection? And we already emphasized this many times. We want to generalize well. We want to do prediction, classification, or regression better, because so it's when you select less features and only the good features, the model is less sensitive to noise. And using the language of the learning theorem is the model has lower variance. And I will explain what do I mean lower variance later, but just keep that in mind is variance here normally means if my training data just has a little bit shift by adding some samples or by removing some samples, my model will be still quite similar. This type of model means low variance model. But if your training data just by adding a little bit noise and your model completely change a lot, that means high variance models. And when you have a lot of features, actually the variance is quite high in the model, but I'm going to explain later. So this is still just intuitive introductions. Also, computational scalability and efficiency, we emphasized many times before. Of course, it's a smaller matrix, right? Of course, it's more efficient in terms of the memory cost or space cost. And if you remember that type of vector with computation, when you have a smaller P to P prime, of course, the computation cost, timing cost also got smaller. Question there? Okay. And then the last one is about interpretability. And this we emphasize many times because you have less features, it's easier to understand the features, understand the weights, just like the example we showed, right? The features, how the feature contributes to the money, to the revenue of the movie. if you have a huge number of features selected, it's really hard for the domain expert even to understand. And we want to have sparse models, fewer features, important features, just important features selected. So now is how do you do the feature selection? There are three groups of approach. The first is called filtering approach. You want to rank the features independently from the predictor you want to use, and just based on, you either just select one feature at a time based on maybe correlations of the feature to the target labels. And that's just a very classic approach how to select features. Or you select a set of features based on their relationship to the target variables. That's called a multi-variate filtering approach. So there's also a second category of feature selection called a wrapper approach. So wrapper approach uses a predictor. It's a wrapper on top of a predictor. So you try to use the predictor to evaluate, is that set of feature important or not important? And there's a search flavor in both the wrapper whenever you try to select not just univariate features of, if you want to select subsets of features, and or like here or there, multivariate filtering approach, there's always an issue of search. What subset you search out of the P, a set of P features. So I'm going to explain it more detailed later. And the last category is the embedding, which is lasso. Lasso is a method. It's a single model can perform feature selection and prediction just using one model. There's no separate wrapper feature selection and then learning the predictor steps at all. Just the lasso itself can select feature and perform prediction just using one model. So this is called embedding approach. Question here? All right, so now group, sure.
So the first one, it says ranks features independently of the predictor. So how does
there's
it rank?
no predictor at all.
So on what basis does it rank?
Yes, so that's exactly the next page about. All right, so how do you rank features? If not using a predictor, you have to use some kind of evaluation metric, right? There are some classic metrics in the literature. So for example, the very classic metric is called correlation metric. This is the Pearson correlation, and I hope you learned it in your maybe probability 1 class. Yeah, maybe 2 or statistic 1. So this really just the covariance of this feature versus the y variable. So the upper is calculation of covariance. So this is just the covariance between this xi this x variable versus the y variable over the variance. So here xi, yi means the samples. And so this is the feature x. Then if you have feature z, then use correlation just to, so in the end, correlation is just a normalized covariance. So assuming you have a data is x and z and other features. Yeah, it's a little confusing that we use x and z here, so yeah, so in the end, so let's just assume a very simple case. I have a f function. I'm trying to predict f function from a 2-feature input space into the output space y. And we treat X feature and Z feature, they're just random variables. Y output is also random variable. Then I'm just calculating the correlation of X and Y, and also Z and Y. If correlation of X and Y larger than correlation of Z and Y, if I can only train a model with only one features, I'm going to get rid of the Z features, because the correlation of X and Y is higher than the correlation of Z and Y. Questions? And the equation is there. I don't want to explain it because this is, you should already learned in the basic probability class. Covariance over normalized. Sure.
What if there are more than two features then?
And you just, assuming you have x1 to xp features, x1, x2, going to xp, and then you just do correlation of x1y, x2y, x2 onto xpy, you rank them. You pick the top, assuming D features, but that's how many D, it depends on you. This is the generic situation. This is the simplest situation. Only two features. So you can tell sometimes I write very quickly, and then maybe later you cannot tell my my handwritten notes. So hopefully you can get it later. I just going to add a little bit more notes. Okay, so very simple. So why correlation? Because correlation is, first of all, it captures the relationship, linear relationship of a feature and the target variable. And also this correlation metric is unit independent. It's always bounded by -1 to 1. So let's look at the figure. So this shows you a situation. X feature and Y feature are completely positively correlated. So this means Rxy equals to 1. And this right figure shows you equals to 0.5. And this figure shows you there's no correlation at all. So why this is good, if you think about it, why should I pick X features if the correlation of X to Y is 1? Why should I select this feature? Just because its correlation is 1.
And we can get rid of Y feature, just keep X.
Because it's almost equivalent to, when you know X, you know Y. Just really strong relationships, right? Of course, this is an important feature.
And why is -1 not as significant as +1?
This is also important. So the only not important is actually this. Is the absolute value is the importance. Sorry, I understand what you will ask. What I should have is absolute values. Yes, good catch. Yeah, I hope you understand how he got me. He was trying to ask, so if you do this ranking just according to Pearson correlation, and then that means those -1 Pearson correlation will be bad features. That's a good catch. I did something wrong here. We should rank them according to the absolute values of the correlation. And this will guarantee those are close to 0 are bad features. So this is also good feature. Because when you know X, you actually can almost guarantee the -X is the Y. But this is just totally not, right? Because you almost know nothing if you know X, you almost know nothing about Y at all. So those correlations to be really, really low. Actually, we don't, if you, according to just this univariate relationships, we don't want those features. So there's one thing I want to emphasize is there's some distance called cosine used it's a very important distance measure in information retrieval. The cosine is actually just a special case of Pearson correlation. So if you look at this equation, a cosine is just x and y doing in a product, right? If you look at this, if your x vector is actually 0, it means the mean vector of x, if it's 0, y is also 0, and the Pearson correlation is exactly cosine similarity. And cosine, because there's no, so that's just very popular, and I hope there actually should be more discussion about why cosine is a good measure, and so I'm going to leave that out for offline discussions. All right, so that's Pearson correlation. There's another metric called t-test. The t-test is based on some other assumptions. Pearson correlation is about linear correlation of x and y, right? So t-test is actually based on Gaussian distribution. Yeah.
Where you have like x and y.
Yeah.
Yeah. So in this case, y is the output or just another feature? Is y the output or the different
Y
feature?
is the target here. Oh, you mean this cosine
Yeah.
here?
Yeah. When you're calculating the correlation.
Pearson correlation?
Yeah.
Yeah, so that's exactly what I tried to show here. So when you have x and z, two features, I'm trying to project to y, and what you're calculating is x and y, z and y, and then you rank them according to the absolute values of Pearson correlation. And it's a bounded score, which is good. You know when it's good, because when absolute value is 1, you know, yes, that's a very good feature. Not like some other metrics, it's positive infinity to minus infinity. It's very hard to judge. Is it good or it's not good? Because you don't know the upper bound, you don't know the lower bound. All right, so then another metric called t-test. So I hope you still remember what is a Gaussian distribution. So this is actually for classification. So Pearson correlation, majority for regression, and this is for classification. So in a classification, there's actually two hypotheses. You plot that specific feature you care. So in this case, I should just xi feature versus the class like y. And in this case, y have only two classes, -1 and 1. It's for binary classification. So if this feature distributed, you just draw a distribution like a histogram of the x feature. The two distributions, what I mean distribution is those x from the -1 class or those x from the +1 class, if you just plot them by histogram, they totally overlap with each other, which means there's no way I separate the two features, and they tell me nothing about the differences of the two classes. So this is the left part. On the right part, it's different. You see, you can plot those x features on the class 1, those features on the class 2. Actually, this is the -1, this is the +1. You can actually tell, I mean, the two features are distributed quite differently. This actually tells you there are quite significant differences of this feature to tell you about the two classes. So this is the one we prefer, and this is the one we not prefer. We use this intuition to select features. And how do you select? And actually you have to something called student distribution, which I don't want to cover. Hopefully you already learned it in the probability class. So the null hypothesis is your feature, your x feature from the class 1 and x feature from the class 2, their mean is the same or their mean is not the same. And use hypothesis testing to get the p-value to show you, to tells you, and is it even significant against the null hypothesis. And if you haven't learned about hypothesis testing, you really need to learn by yourself. Yeah. So because there's a lot of things behind this, and there's no way I talk about it in 5 minutes. So in the end, it's just this: you through the t-test, it can tells you how significant this feature really is, follows this type of distribution. The two means are very nicely separated. It gives very good signals just from the differences of the mean to tell you the one from one class, the other from the other class. So that's the basic intuition, and there's assumption of each is the Gaussian distribution, and their variance are actually assumed to be this. I think the variance is the same in this case, yes. And there's a lot of variation of this test. There are many variations, which there's no way we cover in the course. But, so in the end, is the distance among the means significant or not? The non-hypothesis is there's no differences at all. So in the end, this just gives you a two simple flavor about univariate base. But you can tell the univariate base really just the x feature versus the y feature. If you have x1 to xp, you need to perform each xi feature versus the y. So maybe let me repeat because this is a little bit too maybe too abstract. So similar to what we just did for the Pearson correlation, where you have x1, x2, to xp features, you perform this test. Let's just write t x1 versus the y, x1 versus x2 versus the y. On 2, xp versus the y. And you rank according to the values it gave you. And yeah. So so that's the univariate based approach, but actually there's a lot more, something called information gain, mutual information. There are many more. So there's a table in a few slides. I summarize the list of univariate features. There are also materials in our reading section about if you want to learn it and where should you read. And then let's move on to multi-variate filtering approach. So multi-variate filtering approach is a lot harder, actually a lot harder compared to univariate-based approach. Because univariate-based approach, what you do is really just single feature versus the y. And then the performance, if you think, is all just an OP cost, cost that pairwise calculation is an OP cost operation. But when you look for to select subsets instead of each at a time and rank them through ranking, and the problem really comes to how do you select the subsets? And how do you even evaluate the subsets? So the evaluation of the subsets, there are a lot of metrics too, called group correlation or something called marker blanket, which has a lot of things behind. I'm not going to cover. And what I want to emphasize today is about how do you select subsets. So why do I even want to select a subset instead of using the univariate approach, right? Because hopefully just it can help me filter out the bad ones and just leave all the good ones from univariate xi versus y. So this figure gives you a very classic reason why we want to select subsets. Who can give me a guess? So let's just use the correlation, or actually, yeah, this is a classification. So you can actually tell if you use this, the t-test intuitions I just showed you. So forget about, so this is the x1 feature, this is the x2 feature, and the star versus the circle means two classes, and also the color, yellow or red, means two classes. Assuming I'm doing univariate feature selection, so I'm trying to select x1 feature according to its relationship to the two classes. So you don't even need to look at everything above. You only need to look this surrounding regions, because you only consider x1, right? If you only consider x1, the star and the circle will completely overlap with each other if you only consider x1. I hope you understand that. So who has question about this? If you only look at feature 1, which equivalent to you project the features, project everything down to the x1 coordinate, that just single coordinate, which on the x1, from left to right, these are the yellow, maybe class 1, and the red class 2. They completely overlap with each other. Same thing happened for on x2, right? You just project everything onto x2 because I only look at x2 and y, right? So that's exactly what we try to say, univariate. Well, how do you do univariate? T x1 versus the y. T x2 versus the y. And it can tell you, it tells me nothing if I only look at x1 to separate the two classes, to separate the green versus the red. And the same thing happened in x2. If I only look at x2 coordinate from the lower to the upper, and all these two classes, green and red, completely overlap. But actually you can tell these two classes are very nicely separated through some kind of combination of x1 and x2. If I can write, you either just simple line x1 plus x2, but that's not the best. But actually the good feature is, assuming this is C1, this is C2, x1 minus C1 times x2 minus C2. It's almost the best feature, right? x1 minus c1, so this gives me like a minus on this side, and this gives me a minus on the downside. If the multiplication is positive, that's a red class. If the multiplication is negative, it's the green class. That's the best classifier ever. So this actually tells you the interaction among the x1 and x2 is important. It's almost the best feature in this case. But if you use univariate feature selection, you're going to miss the best classifier using that interaction term. Question here? Yeah. So now if I tell you there are x1, x2, up to maybe x10 features, and actually is the something like x3 and x4 interaction term is the most important features. And how do you even select this without, in the beginning, like, I do not know, is like 3 features or 2 features or 4 features or even maybe 10 features all interact together, right? So what's the search operation of O? I want to select. I want to know the subset. Which subset give me, hopefully there's some kind of evaluation metrics to give me which feature is good versus why, or which feature is bad. So maybe let me write that the other way. It's X selected, I1, so it's hard to know even how many. So in the end, so how do I represent a subset? How do I represent a subset? I'm trying to select a subset from X1 to XP. What is a simple strategy to show who is selected, who is not selected? It's a binary flag, right? I want to have a binary flag on each. It's a theta vector. If it's selected, it's 1. If it's not selected, it's 0. And this is a p-dimensional vector. So in the end, if you think about it, subset selection is a task looking for a theta vector. Theta binary vector. And that indicating how do you select. Okay, so what's the size of the theta vector? Possible size. Two to the p, right? Because for each position there are 2 choices, there are total p positions. 2 to the p. Which means, how do I select it? I need to enumerate every one of the 2 to the p choices if I want to do a complete good search about good possible subsets. And the cost is extremely high because it's exponential, right? 2 to the p. And we don't even consider how do you do assessment of each of that theta, selected theta parameter, and then you got those features, and then you need to perform the evaluation step, right? So that also has a lot of cost. So this is O2 to the p times the cost of evaluating a specific theta. This search space is extremely large. And yeah, of course, 2 to the p, right? All right, so, but still, like, this type of feature are very, very important. For example, in the situation like text sentiment classification, you want to read a product as good or bad or neutral. And so, of course, you don't want to just use the single feature like good, and those combination feature like not good, you have to treat not good together as a feature, right? It's very necessary to evaluate the combination of words in this case, not just single words, but combination of words. Question about this? I feel a little bit dry. You're a little confused now by now. So words, n-gram, if you think about n-gram, it's a type of feature combination. A-gram, like, so very good, very, 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 very good, or not very boring, like fantastically interesting, and all those type of combinations. For sentiment classification, the combination matters. So what I was trying to show is, if you do univariate, it's highly likely than not, it's highly correlated with the negative sentiments. But if that's like not boring, think about not boring, and if you only just do not boring actually is positive sentiment, right? It's an interaction, it's an important subset to search for, and we have to model or search. But the search space extremely large is OP2 to the P. So especially you might think like 2 to the P is not large, right? Let's think about our word example. What's the P here? It's, if you're a native speaker or whoever work on NLP, whoever worked what should it be the P roughly? Actually 30,000. 30,000 is the minimal number you normally use. P in this case is actually roughly 30,000. 2 to the 30,000. All right, so this is just how do you perform a multivariate subset feature selection. You need 2 different modules. The first module is a measure for evaluating that subset. The second module is a strategy to search that subset. So based on what we represented, you need to be able to evaluate theta, and you also need to be able to search theta. And of course, it's NP hard. So you can actually plot that search, all the search through this DAG structure, directed acyclic graph. And this includes all the 2 to the P, and it's a path from 0, 0, 0 to 1, 1, 1. This 0, 0, 0 means no feature is selected. 1, 1, 1 means all the features are selected. If you only allow 1 mutation on the binary vector, this gives you P. The first layer is P. There are P different theta. And second layer is, you can keep, so it's actually pretty easy to P, and then all the possible paths. In the end, the summation is 2 to the P. In the end, you're trying to search on this DAG structure. And there's actually no way you enumerate one just a P, just a little bit large. There are many different greedy or heuristic-driven search. I think I had it later, so I had it in the next wrapper approach, because wrapper approach is mostly subset-based approach. So I'm going to cover that. So this, before I move to wrapper, the filtering approach is, the summary is, it's really very fast because it's more a simple statistic-based, correlation-based analysis, and it provides generic selection of features. It's more a predictor agnostic. It doesn't couple with any predictor at all. But that's also one of the criticism people question about this type of approach, because it's not optimized to a specific predictor. It's very generic. And it's actually still used a lot as pre-processing because fast and intuitive. And this is a list, and feel free to check it out after in Scikit-learn. There's a lot of filtering-based approach already implemented. And I'm going to put the API, so hopefully you have time to read those, what are implemented there. So